Well, hi and welcome everybody. In this video, I want to record at least one, maybe two examples of transformational arguments, the likes of which you might have to do in a discussion. These are transformational arguments. And this is a question I've asked of young adults before. We're going to suppose that there are a couple of right angles in that picture and that EH is an angle bisector for angle REN, and those are the only things we're assuming. And we're going to give a transformational argument as to why triangle HEN is congruent to triangle HER. That is to say, we're going to describe an isometry that maps triangle hen onto triangle her, and then we're going to justify why the isometry is correct. Now, we know that our triangles are congruent, if we're careful, by angle, angle, side. But remember that this part of our course imagines that we never had side angle side or angle angle side or any of those, and we instead postulate the reflection postulate. So we're going to run a transformation-based argument as to why the two triangles are congruent. And the way we do that is we map triangle hen onto triangle her, and we show H maps onto H, E maps onto E, N maps onto R. That's the idea. Now, what's the transformation that probably does that? Well, the transformation that probably does that is a reflection over line HE. If we were to reflect triangle HEN over line HE, it ends up on triangle HER, and we will prove that. So I'm not going to write all the setup down. I mean, that's not something for this video, but all that given information ends up here, and we will show that triangle HEN is congruent to triangle HER. Those are all things that you can write. I don't have to write those in an instructional video. I will say, let's consider the reflection in line HE of triangle HEN, which we will call triangle H prime E prime N prime. We will show that H prime is H, E prime is E, and N prime is R. That's the idea. Our job is to show that when we pick things up and put them down, every vertex we want lines up with every vertex we want. Now, two of these are really easy. Two of these are really, really easy. I need a way to extend page. I'll pause a moment. I am not able to extend the page. There will be a little bit of back and forth here, and that's okay. Because H and E are on the reflection line, it follows that H prime is in fact H and E prime is in fact E. This is one of the properties we looked at, that when we reflect, all the points on the line remain on the line. But what about the other point? Well, we've got to show that N ends up on R. Well, how do we do that? We know by side switching that angle HEN ends up on angle HER. That's side switching. So let's say that. By side switching, that's false. E prime N prime is the ray ER. Why? Because by side switching, the rays of the angle reflect over the angle bisector, the one becomes the other. That's how side switching worked. So ray E prime N prime is the ray ER. But that doesn't mean that N prime is R necessarily. It just means that N prime is somewhere along here. Maybe N prime is here. Maybe N prime is here. We kinda hope that N prime is there. We have no other information in the question to use, and so now we've got to run through the possibilities. What goes wrong if N prime is between E and R? Well, we know that that angle is a right angle, but we also know that angle ERH is a right angle. So this is going to be a problem for us. If N prime is between E and R, then we have a perpendicular here and also a perpendicular here. That is trouble. That's going to be a contradiction. So let's say that. Let's find a way to say that. Suppose that N prime is between E and R. Notice that angle HN prime E is a right angle because isometries preserve angle measure. Right? However, angle HN prime E is an exterior angle to triangle HRN prime. And angle HRN prime is right. This contradicts the exterior angle theorem. Well, what goes wrong in the other case? In the other case, you have a right angle here, and then angle HRE is an exterior angle of triangle NH prime R, and this also violates the exterior angle theorem. So, a similar contradiction arises if R is between E and N prime. Thus, N prime is R. Because there exists an isometry such that H prime equals H, E prime equals E, and N prime equals R, triangle HEN is congruent to triangle HER as needed. The goal in each of these proofs is to establish that there is an isometry that does the job, and then to show how it does the job. I'll do one more of these in a separate video in case you need a second example. and that'll be another 10 minutes of your time.